My name is Robert Ramey, and let's have a look here. The title, first of all, I'd like to thank you for coming. The title of my presentation is C++, Abstract Algebra and Applications. I've been an active member of Boost since 2003. My claim to fame in Boost is in large part the Boost serialization library. I'm the designer and maintainer of the Boost library incubator, and that's how I spend my time, is related to C++ that other people would know about. So I'm here to talk about C++, abstract algebra, and applications. Let's look at just a simple program here. How can this thing fail? That's, yeah, okay, interesting. I have to be able to get out here and see it. So, this is a trivial program. It's a one-liner. So, it's hard to imagine how somebody could make a mistake with this program. And yet, it happens all the time. Somebody might have fed in values for L and W, length and width. If somebody had chosen one that's a negative value, then the product of those is going to be a negative value, and you can't have a perimeter of a rectangle which is negative value. You've got, it could be, if somebody fed you a value which is not a floating point number, a nan, then the result is going to be a nan. It could be that somebody fed you values, or this is part of a subroutine that takes arguments, and one of the arguments is in meters and the other's in feet. So you're thinking, well, that's kind of beyond our scope. I'm going to argue, number one, that it isn't, and that we do have methods that can address these kinds of errors. I also believe that many of our what we call our debugging situations are not really arcane issues like we got our matrix inversion wrong. Oftentimes, many times, they have their origin in questions exactly like this. So the question is, how can we as programmers make progress on this? So first, I'm going to, there we go, talk a little bit about what it means for a correct program. There's academic definitions, and there's been a lot of discussion about it. I'm not going to get there quite yet. I'm going to talk about what happens when you program an ABS system and somebody gets killed with it. I'm talking about when you talk to your boss and then you deliver the product and it doesn't work the way he thought it was going to work. In that sense, the program is incorrect. And I've defined a couple different levels. And starting level 0, it's, does the thing really do what everybody agrees it should do? And I've given a couple examples. A heart pacemaker has to keep some guy's heart beating. And F-35 fighter jet has to shout to the pilot if he's in a stall. There's all sorts. This is really a criteria whether the program is working or not. And proof at this level means that there has to be an agreement ahead of time what the thing is supposed to do. It's amazingly common that we start work and we don't discover until we're 60 or 70% through that actually we weren't on the same page as far as what it takes to call the thing working. And it's extremely common. It's so common that people don't even realize they're doing it. They call it, at the programmer level, they say they changed the spec on me. And at the management level, they say they're a bunch of yo-yos. But what it really means is we got started before we were going to really decide what we were going to do. This is not a mathematical question. But hopefully, if you can get that squared away, or if you think about that next time you talk with some higher up, or at least somebody that's paid more than you, that about what the job is, you can get past that and get a succinct description of what it is you're trying to accomplish. And the next level down, you'll usually take the description that you've been given or you've agreed upon and cast it into some sort of formal model. If you're in a finance environment, you might talk in terms of an accounting system, debits, credits, balances, reports, etc., that are based on this. That's really kind of a language. If you're in the engineering world, you might talk in terms of differential equations or solving for differential equations or approximating functions or whatever. You have a language. You're not even to the computer programming part yet. You're really working with a formal model of the phenomenon which you started with. And as I say, this goes beyond math. It goes, for example, if you're working in a place like a place that's making tax preparation software, you're going to have some model or some description of the tax code in some formal way that you can actually talk about it and that you can actually turn that into some sort of computer program. Might be a list of rules. It might be just a list of rules in your own native language, but are restricted to a set that resolves the ambiguity. If you start programming without that, then of course you will be in a cycle, because you'll be in a situation that you'll program something and we won't be agreeing on what it is. But we're actually quite familiar with this, and this is usually the case. In the scientific area, this is very, very well known. We know how we get code that inverts matrices and solves differential equations. And this is, the algorithms can be pretty complex, but they're all agreed upon. At the next level, we take that formal model and we turn it into an approximation of the formal model. For example, if we're looking at an engineering problem, we describe it in differential equations, limits, real numbers, things like that. In our computers, we don't have real numbers. We have floating point numbers, but they're really only an approximation to real numbers. The whole area of numerical analysis addresses this problem, that when we actually try to use these approximations to a real number, we get things like round-off error, error accumulation, and precision evaporating. And there's a whole branch of applied mathematics, which is numerical analysis, which addresses this. I'm sure I'd have to think about it a little bit more, but in the accounting field, I'm sure that somebody's made an accounting system and they determined that, well, $1 billion is going to be enough. And wait a minute, of course, since we're suffering from at least 1,000 years of chronic inflation, they eventually get it wrong. So their mathematical or their computerized model is at a variance with the reality, and it eventually may come up. And I'm sure that we could find similar situations for the other examples that I gave. So at this level, if we want to get a correct program, we're going to have to generate an approximation to our formal model, which actually reflects that formal model. And I'm going to argue that it has to be able to detect when our informal model breaks down. If we want our program to be really correct, it has to detect overflows. That's nothing wrong with it. That's nothing related to the base algorithm. That's our computer implementation. And so we can't really consider our program correct if some guy pulls a stick on his fighter jet and nothing happens. We can say, well, hey, it overflowed. Not my problem. It is our problem. So in the final level, I say program code. And program code is basically you write the code, and I'll be damned, you can write the code, you think you understand the problem, you think you understand the formal model, you take into account the realities and vagaries of computer hardware, and you still make a mistake. You might put parentheses in the wrong place. You might implicitly promote one variable from one type to another. You might do all sorts of things of that nature. And it's easy to say that it's your responsibility to know enough not to do that. It's extremely easy to do. We do it all the time. And a large part of our debugging effort is also spent on chasing down almost trivial errors of that nature. So if we want to get a correct program, we've got a big job here. So the history of program correctness really, in my view, started with a paper written by Anthony Hoare called, I'm not sure, does anyone know how you really pronounce that guy's last name to avoid creating some sort of scandal? Okay, I call him Anthony Hoare. And the idea was to take the techniques of program proving and applying them to create a provably correct computer program. This was a hugely popular idea. It's probably spawned 1,000 papers. It spawned things like GoTo considered harmful. It spawned structured programming. It spawned design by contract. And so it's been tremendously influential. To this day, it's not really disputed as the way to think about a provably correct program. And let's just take a look at, and the way this works is, he defined, I'm not going to go through this in detail because you could do it on your own, and I don't have time, and I think that I'll give you just enough. And what he did was he described certain logical rules about how a program changes the situation of the program state. And I'm going to just describe one rule, and that is composition. And what he said here, I can't see the slide here, is this rule basically says if I have two statements which are correct, if I compose them together, then they'll still be correct. And he formalized that idea by the first statement. We start with a certain proposition which is true. We execute a statement Q1, and then that results in a new proposition which is true. So for example, if I say A plus B equals C, then I know that A and B are valid arguments. If I add those together and get a result, then that will also be a valid result. And he said, okay, and if I take a number X and multiply it, and then the second proposition might be something like if I take a value like X and multiply it by 4, and then X is a valid number, the product will be a valid number. So if I compose those two statements into multiply A plus B times 4, then by this line of reasoning, then I will guarantee that the final result will be correct. So what he's done is to say, I make up a logic rule, and if I apply it to demonstrably or provably correct propositions, the result will also create a new fact. And that fact will be a new proposition that I can use subsequently in the program. Now that's kind of a crude explanation because I'm not a mathematician, I'm kind of a crude guy, but I think that we can see what this idea is, how we sort of already apply it intuitively, and how this could be built upon and expanded to cover an arbitrarily large program. He's in the original paper, which in my view is still the best on the subject. He stated, I think, either 4 or 5 rules. One was composition, that's this one. Another one is assignment. He did do one on iteration, and then there was some other one. And if you're interested, when you get the slides, you can look through it. But it's basically, this is pretty much all there is to the method. And there's a couple things that come out of this. Program correctness and the program itself are not the same thing. Or what I mean to say is program proof and the program are not the same thing. In the literature, there seems to be the idea sometimes that if we write the proof, then we can turn it into a program in a mechanical way. And I don't believe that's the case. There's some kinds of proofs that definitely can't be done. A proof by contradiction can't be turned into a computer program to generate a result. You'd have to limit yourself to constructive proofs. In any case, what we see here is we don't really see the progression of the proof. We do see progression of the proof, but it's in parallel to the expressions we're executing. So we're generating results on one side of the T, and we're putting the justifications on the right side of the T. They're different things, and it's better to not get them confused. So, now once you've got this idea, and we've got in C++ the concept of subroutines or functions, and if you have a provably correct function module, then of course that's really a long composition. So now you have what really is analogous in the math world to a theorem, where so if you start with some true propositions, you invoke the function, you get a result which you know has got to be true. And when you use that in some other level, then you can look at that level just at that level without having to go back and check this other one, because you know either you or somebody else has proved it. This is the idea. The idea is basically sound, I'm going to say in theory, but that's a little unfair. The idea is described as quite sound. It also does one great thing. It changes our thinking from what they call operationally to logically, in the sense I'm not really thinking, once I do this, I'm not really thinking about all the details of how the result is produced. Once I've encapsulated that, I'm really thinking it is just a single transformation, and I can abstract away a lot of the detail of my program. In his examples that he used, he only addressed immutable functions in this particular paper. That might not be quite true, but it's almost true. And he kind of failed to address a lot of the problems that we create for ourselves these days. So in his world, or the world described in this paper, we're mostly making functions which start out with a value, go to the end, produce a value, and they don't have any side effects or outside influences and things of that nature. Subsequent to this paper, other papers expanded upon this to make it more widely applicable, but it's still basically a variation on the same idea. We don't have to go, if one has nothing else to do, he could track this down and spend a lot of time doing it, but I don't think it would be all that productive. So, it says, so now let's go back and look at our original example. So here's our program that we've attempted. We're C++ programmers. We're attempting to take Hoare's idea and realize it in terms of the tools that we have at our disposal. Well, I made a function. I called it perimeter. Oh, okay. So we start out with the two values L and W. Well, right away we verify that the proposition that we want to start with is that these are values that actually reflect our idea about what length is. This means that they have to be valid floating point numbers, and they have to be numbers that are not negative. So we apply that to the first one, to the length value, and we apply it to the width value, and then the actual perimeter calculation, we don't have to do anything, because that's actually the definition, the mathematical or geometrical definition of perimeter. That if we start with valid length and valid width and we apply this formula, since we can plug in a mathematical definition, we know it's correct by definition. We assign that to the perimeter, but now in order to verify that our computer didn't fail. Mathematically, that's never going to fail. But remember, we're working in the real world. We're not working in the Hoare world where he just talks about the values. He doesn't consider things like overflow and stuff like that. But we're going to expand and broaden our criteria for a correct program. So at that point, the final result, we want to verify. We know it can't be negative because that's the way our hardware works. But it is possible for it to overflow. So then we would have to check this. So now we would have a function that we have, or I would submit, we proved that it produces a correct result. So let me take a drink of water. Did I make the slide wrong?
Oh, yeah, it says area, but I think you meant
Now, that's actually a really good point. And I'm sure I made a mistake, but you caught it just by looking at the code. That's what it's all about here. I'm trying to write code that is visibly and demonstrably correct by looking at it. So I guess you're backing me up here.
the compiler would have caught that.
Huh?
The compiler would have caught that.
Well, was it not just a comment?
No, it's the variable name is different.
You're asking if area is an and using the
Yeah, so you're correct. Compiler would have caught that. That's good. But anyway, certainly that wasn't my intention. But anyway, well, now I believe that on floating point, the infinity is a particular type of NAND, but you might correct me if I'm wrong. No? It is? Okay. It's not a number, but it's an invalid number. Is that changed since 1970? Yeah. Okay. Well, there you go. Now that's kind of an interesting side issue as well. By actually making our propositions visible in this way, it becomes clear that I have a mistake here, which normally wouldn't occur. All right. Now, this theory or this idea got caught on big time in the whole academic world, and they flogged it for many years without much success for people like us, and to the point where the academicians got pretty frustrated with us. I'll let you read this for yourself. I don't have anything to say for it, except it didn't help me much. So we're not on the same page here, right, guys? That's the source of our problem. They have a good idea, but for whatever, when I try to apply it, it's not going to work out. And we can see from the previous example that if we coded everything like that, we would never accomplish anything. So now we're in this quandary. We're writing code that we know can't be correct, or we know is likely got a lot of bugs in it. It's just, a matter of fact, I couldn't even write the code according to the prescription here without putting a couple bugs in it. So anyway, that's where our bugs come from. That's one of the places where our bugs come from. So eventually, and this was in 1985-ish, somebody came up, or Bertrand Meyer specifically, tried to throw us a bone, and I don't know if he would see it this way, but in my view, it's a direct descendant of the Hoare proof concept, where you start out with initial propositions. As you proceed through the execution of the program, you develop a new set of true propositions which can be used subsequently, and then finally, you know that at the very end, you end up with a true result. And this turns out in the C++ world to be the assert statement. And we've got it in the standard, and people use it, people don't use it. In order to get over our complaint that this is too too intensive, costs too much resources and execution time, they define this in such a way that these checks are only done on a debug release and not on a release. So this was a compromise. Okay, we're going to give you the method to prove that your functions are correct, and since you're complaining about the performance, we're going to suppress them when you release the code. Well, you know, that wasn't a bad compromise. It was the only realistic thing to do if you wanted to get some program correctness. But still, for whatever reason, I think it had some success. I don't know. I'm a freelance programmer. I've never walked into a company where I saw them use design by contract, but there may be some out there. But now it's 2016. We can do better. We have C++. And we can address some of the issues associated with trying to make a correct program. One problem with the Bertrand-Meyer approach, or the design by contract, and actually the Hoare one as well, was that every time we call a function, we'd be repeating the same checks on the same parameters. If we factored out a function or split it or divided it into a couple, then we end up doing all the checks all over again on the next functions, the next level down. And so the better code we make, the better we factor our code, the slower it's going to be. And this is kind of unattractive, but C++ gives us the tool of the type system. So when I can define a length type, before I was using floats, but I'm going to define here a length type, and that I think it's pretty apparent what this does. Once I initialize it, it's guaranteed to be correct. It's generally not used in such a way. There are no functions here which can mutate it. So anytime that I create a length, then I know when I use that, I don't have to do any precondition checking because it's all checked and it can't change. So when I then start using this, let's have a look here. And we got an extra bonus too. These days we can use the const expert functionality. So it gets all done at compile time. So where we have a zero runtime overhead proof that this contains a valid number. If we insert a literal, it's going to be all checked at compile time. It's zero runtime cost. If we create this thing at execution time, this particular instance needs to be only checked when it's created. Henceforth and forevermore, it never has to be checked again because it fits our concept or idea about what a length is. So now, what happens when we look at our program again? We're given a rectangle with the dimensions L and W. This time it's passing arguments of type length. They could be constant references, they could be values, it doesn't matter. Preconditions, well, we don't really need any because we know that the values we're passing are correct because the way we defined them and the way we constructed them. The actual calculation we know is correct by definition. I did have to factor it or express it slightly differently because the original length type that I created only defined one operator, and that was the plus operator. So I can't multiply a length by anything, which is probably a good thing because if I'm multiplying two lengths in the idea that I'm going to get another length, I'm probably making a mistake somewhere. I've restricted the legal operations to those that I know I'm intending to for length to have in this context. So if I just write by accident, I mistakenly put an asterisk instead of a plus sign, whoops, going to get a compile time error there too. So, and then I return the perimeter. Now, the sum creates, when I do the addition there of the L plus W, that that returns a new sum, and the function that creates that sum checks its result. So I know that the result of that is actually a legal length, and then when it's copied over or assigned to the perimeter, it doesn't have to be checked. The assignment operator doesn't have to do any checking because it only works with a length, an instance of type length, which is already known to be correct. So, anybody like to ask a question about that? Because that's quite a mouthful. Yes?
Just a technical question. I noticed that your plus operator was a const expert. Could this also be made const expert since the only operation?
Sure it could. Because the const expert is kind of, how should I say? If I use const expert, then everything it calls has to be const expert. And this I could just as well make const expert because it depends only on one thing, or actually two things. The length constructor, which I can make const expert, and this arithmetic operation, which actually the syntax might be different. I might have to put const expert before it, and then I would probably have to put const expert on my perimeter function. But I mean, that's good thinking. And then you're saying, well, since we know we're going to exploit the immutability and the restrictions we've placed upon ourselves in order to get more free stuff. Okay, so this is the thrust of, in my view, the modern situation towards program correctness. I think if we use C++ and we think about our types, and that's what I'm going to talk about now, we can use our type system to make progress towards proving our programs correct. All right, so here is our, I'm going to make an identification here. We have our C++ type length, which we've defined. But we could look at this, we could step back a little bit and look at this in a slightly broader way. Or put it a different way, if one of us was a mathematician, which is probably not the case, except for maybe a couple unusual examples. Yeah, there you go, I rest my case. They would think in terms of a length is not a C++ data type, because they don't understand C++. Another exception, of course. But they would say, well, wait a minute. This concept that you've designed is really a set of legal values. You've designed an idea which you call length, and really what it corresponds to is a set of legal values which are real numbers and which are not negative. And that's a legal length. If you're talking about lengths on the planet Earth, they might say, well, but the length has it's the real numbers between two ranges or whatever. But for now, we'll just see the fact that a C++ data type corresponds to a set of values. That value is all the possible instantiations of our C++ type. So when you write a C++ type, you're actually writing a statement out of set theory about, and you're defining a set of values. And the values, that set of values is all the values that your C++ type can take on. So that's pretty much all there is about that. Every time we create a type, we're creating a set of some sort. Now, there's a rabbit hole I could go down to, which is really interesting, which I'm not going to do, is what happens when you have composed types and things like that. That's for really another discussion. So before anybody asks that, which probably won't happen, we're going to focus on just one narrow aspect of what this means. So I'll go over here this time. I have to go over here because my machine shows my notes. It doesn't show this. So we've got the concept of a set, our length. We also have another thing. We have the concept of addition of two members of that set to create a third. We've added our plus function takes any two values of length, adds them together, and produces a third one. This is a binary function. It takes Well, I just described what it does, and it turns out that when you have a set unified or paired with an operation such as this binary operation which returns a value of the same type, that constitutes a well-known structure from the branch of mathematics called abstract algebra. And it turns out that mathematicians have taken the idea of a combination of a set and operation and decided, well, that's a mathematical entity, and I can say something about that in a general way, whether it's the operation is plus, whether the set is the number of is the number of different people in the world, or whatever. There's certain things I can say about that, and it leads to a whole interesting area of mathematics, which we're not going to go into here, but it's still interesting. So, but for us in the real world, we're going to confine ourselves to a relatively small subset. We start with a set. It can include a plus function, and that becomes what they call a semigroup. And it's a semigroup because the function is associative. Even that I'm not going to touch upon here because I don't want to get bogged down. But in any case, if you start with a set and you add a function to it, then you get a semigroup. If you say, besides that, we're going to add an identity function, a concept of a zero, so that a plus 0 is equal to a. Not every set has that property. If you take zip codes, well, there's no concept of a zero zip code, or there's no concept of even adding zip codes. So zip codes would stop here at being a set. Another operation is the inverse. So if I take, for example, prices, and I have a price list on my menu. Menu is not a good example. Let's just say a price list in the supermarket. I've got apples, oranges. Those constitute a set of values, prices. I can't add two prices together and get anything meaningful. So if I made a type for prices, I wouldn't include the addition operation. But on the other hand, somebody comes along, wait a minute here. Price is not really what I want. I want accounting values. So you can have a debit balance, and you can add 0 to it. I mean, somebody could have a transaction where you give something for free and they debit your account 0, and then the value stays the same. So in an accounting world, this would, if you follow the tree down here, you'd start out with a set. It's a set of values. You would say it has the concept of an addition operator, so it's at least a semigroup. Then you go down and say, it has an identity value because you have a 0. And oh, by the way, it has an inverse operator because you can take, somebody could say, you don't have a positive balance, you have a credit balance on our books. So you've got a negative value. Now, when you learn this in school about math, they talk in terms of real numbers and all of that. That's not bad. In a sense, it's simpler. But the reason I'm talking about using the examples I'm using is to relate it about stuff that we're doing every day. So if you're working in a financial industry or something like this, and you're creating somebody's balance, well, one thing you probably don't want is to multiply two balances together, because all of a sudden we're outside the realm of what we're talking about. We're doing an operation which isn't defined for balances, for accounting balances. They're both numbers, so if I tried to explain it in terms of numbers, it would get really confusing to say, well, some numbers you can add, but other numbers let's think about what we're really talking about. And now you can already kind of see, or hopefully you can see, how this impacts upon the concept of your correct program. You get something that starts to get fairly complicated, and you start throwing these formulas all around, and it's extremely easy to get confused and scale something wrong or do an operation that doesn't make sense. Instead of writing the expression, seeing if it compiles, moving along, and then wait until the company paid out $100 billion, we're going to say, no, we're going to define ahead of time we're going to restrict the operations to only that which makes sense. So the minute we accidentally break a rule, we're going to catch it right on the spot. Now this happens at all compile time in C++. So it's free. No audience reaction from that. I guess I'll take that as a good idea then. Yeah. Huh? It's, I'm wondering if it sounds like when I explain it, it seems so obvious. Maybe it does.
So for your associative operation, where a plus b plus c is equal to a plus b plus c, that's not going to work for a floating point operation. You can't have an associative set of floating points.
Well, that would be a surprise to me.
Correct,
but remember, if we have our type, which is implemented in terms of floating point, it will check the error either at the first or second addition.
So here's the thing, depending on the order that you add values, you can end up with a valid value or an invalid value.
In the example that I wrote for the length, it doesn't, if you break the rules, it doesn't return any value at all. It throws an interrupt. So now you touched on an extremely interesting point. I'm not going much into that here, but I've defined all the valid operations so that at any point that becomes invalid, the program bails with an exception. So I've kind of skirted the issue on the one you just described. But now you provoked me, and I'm going to talk just a little bit about that. If I have a zip code class, well, we can all imagine what a legal zip code class is going to look like. It's going to have an integer, and it's going to have some form of every time we initialize it with an integer or create a new instance of it, it's going to check the list of legal zip codes, right? We're all going to do that. And now all of a sudden, somebody comes along and says, hey, wait a minute, guys, you really dropped the ball. You're requiring a legal zip code here. And we say, sure we are, because we want to sort it and this and that. And say, no. But some people come in here and they're from foreign countries. Or they fill out the form and it's illegible. So then we say, no, okay, well, we're going to fix that. We're going to create our zip code is going to be a variant. And the variant is going to say illegible or foreign country or a legal zip code. But now when you define the plus operation, you have to really think about what the heck we're going to do when somebody tries to compare a legal zip code against one of these other things. Maybe we decide, that's wrong. I mean, there's no way we can recover from that. It indicates somebody dropped the ball somewhere. So we're going to stop there, and we're going to throw an exception right there. We won't even permit the thing to be sorted when you invoke. So it's not going to be an ordered set. So then we're bringing our whole discussion back to the framework of abstract algebra instead of having an argument about what's supposed to happen. I mean, it's not a specialized argument. It's more of a general argument. How are we going to handle things that don't make sense? Because here we built in the concept of what it makes sense for zip code. So, but you hit a very interesting point is I've defined my operations saying they're going to bail anytime it's invalid. But you can also define them in such a way, for example, a floating point number, you can add two nans, and depending on the compiler flags, you won't get any interrupt. And you can say, actually, it's valid to have a nan as a result. And then you can create your algebra on that basis. But you won't get the benefit I'm hoping to promote here, because then you'll have to check it every time. But it's a decision you can make, and you'll be able to make it consciously instead of on an ad hoc basis all over the program. Because we have the checking in one spot, or we don't have the checking in that spot. And everything will be consistent, and it will be thought out in terms of what it really means. If you permit nans, well, wait a minute, it can't be ordered anymore. Or what is a nan? Is a nan a value we don't know? Or is it a value that's the result of some invalid operation? You have to think about that. Any case, all right, I got carried away. Sorry about that. All right, so our type length, if we really fill it out, and if we want to make our type length fulfill the requirements of that the semigroup demands, it needs to support the equality operator, it needs to support the plus operator, and I've also added another requirement which is really outside the scope of abstract algebra itself, of the set being ordered. In order to support that, it should support the 4 C++ operators for comparison. So that's what our length would look like if we fleshed it out. And we'd be in business. So the question is, when I make my new type and I want to verify that it fulfills one of the nodes on that tree of valid objects, then I created a header file which has some type traits defined in it and verifies the existence of these operators. So if it's equality comparable, verifies the existence of the equal and not equal operator. The is less than, or let's take another one, is additive, verifies the existence of the addition operator. So if I want to make my type and fill it out and then verify that it fulfills or it has the operator, or if I include a function and I want to include a precondition saying, aha, this function really only makes sense if you're calling it with a type which models a monoid, then it should support the identity operator. And you can put a static assert right there and verify and prove that your function is being called with a correct parameter at compile time. So that's one more way we can put more information in our program to verify that the function, the parameters being passed are actually fulfilling the requirements we anticipate. But that's still slightly annoying because I wanted something that was just slightly better, and I can construct very simply with a C++ 11 or whatever it is alias to say I've defined an ordered set if the following 2 type traits are true. So I basically can say an ordered set is any type which is both equality comparable and is ordered. So now I have a new concept which I've defined, or a new type trait, which is an ordered set, and I've easily defined it this way. It's just an alias, and it's exactly what I want in order to get what I want next. So this same header algebra then now can, if I make a type and I want to say I want it to model a monoid, well, all I have to do is include a static assert in there and said, is it, if it's a additive monoid? And if I put is additive monoid length and in a static assert, that static assert will pass and will not trip at compile time. If I overlook one of the key functions, for example, if I were to overlook the plus function, the addition function, then I would get a compile time error right at that point. So we have a mechanism now, to recap a little bit. The theory is we have a way of proving programs, which is impractical. We now have tried to make that practical by including the checking in the types. We've tried to regularize our type creation by borrowing from the concepts of abstract algebra. We've added then type traits that we can use to verify in compile time that our types actually do model those concepts. That's where we are now, and that's how we got here. So, still, our length is, let's have a look here. Here's our length, and it's still a little bit of a pain to specify all those functions. So we're going to make it easier by using a little template metaprogramming and the what's it called? Commonly recurring, curiously recurring template pattern. And those of you who can say this better will recognize it right here. And I only have to define some basic operations, and I will derive, I can use private derivation to derive from the additive monoid of the length and the ordered implementation. And so if even though my type, it starts to get kind of elaborate, it also would be a source of error for one to try and specify all the functions for the length type when they're actually all related to each other. Here, in this case, what you would do is you just define the less than, and then this class will generate for you the definitions of the less than or equal, the greater than or equal, etc. So this is a convenience to eliminate the tedium and the source of error of creating types to model any of these concepts or any of these nodes on this tree of algebraic, of abstract algebra types. So, all right. So, actually I kind of jumped ahead and I kind of summarized where we were because I was afraid I was going to run out of time. But fortunately, that seems like it's not going to happen. I propose that this method of using our types to implement these ideas will detect conceptual errors much, much sooner than we normally do. I believe it's easy to include this information when we build our program. Including this information when we build our program requires us to discuss among the other parties exactly what our types are really going to do, rather than waiting for us to code it and for the program to crash. And I also contend that it implements program proof in a practical, reasonable, and a practical way that has relatively little or either no or reasonable impact on the execution time. And of course, it diminishes debug time. And I also believe that it diminishes maintenance effort by a huge amount. When somebody else goes and makes a change, the original assumptions are already all checked in there by static asserts. And so that's my theory here. And I'm going to say one other thing, that this has only scratched the surface of what I believe that this can do. I had to fit it into an hour. This extends to other aspects of C++, which I have not addressed here, in a more powerful and useful way than this. And that's all I'm going to say. I'm working on a book on the subject, which hopefully will come out next year. And this is just one small part of it. And I think that sums it up. And I'm really happy to see so many people here. And I'm available for questions if anybody has something to ask. Yes, sir. Speak up, please.
So your length class at the moment doesn't model units within the framework of abstract algebra. How would you continue to model units without including, like in the same style that you model?
What do you mean by unit?
I mean adding a meter and a...
Aha. That's actually, it's interesting you mentioned that. That was a subject which was addressed. The question is, how does this relate to the concept of dimensional analysis and units? That's right now a separate Boost library. Barton and Nackman, who wrote the book that inspired me on this, and this was written in 1995-ish, I believe, they had a section on this. It is related, but it's related in a way that's slightly unobvious, so I don't feel comfortable answering the question right now. But you are correct in that they're wrestling with the same problem here. And in fact, we haven't touched upon what happens when you want to create an area. Well, you need to multiply two lengths. Well, that doesn't fit into the abstract algebra scheme, but it does fit into the mathematics that deal with it. So this would have to be extended a little bit to address that. But that's a very good point. This is the Boost Units library. I gave a talk on it last year. It's an incredible piece of work. and it's totally inscrutable. So it's a two-edged sword. It makes your program rock solid, but it's agony to figure out how to use it right. Any other question? Yes?
For the derivation of length we had to say forgot, because for people who make mistakes to say include the definition of the addition operator on our type, but we still try to derive from, say, the monoid. Would it kind of like at compile time warn us like, hey, you can't do that?
The question is, let's suppose we overlooked the required operation of plus and expected the code to generate our missing operators. And the question is, would that provide a warning? No, it wouldn't. It would actually stop the compile and provide you with a compile time error, because it refers to a function which should be member of the class and is not there. So it could not be resolved. Bingo. Not only do you get an error, you probably get 50 lines of error messages to help you out. Yes, David?
This is interesting. I like it. The question I have, and I wonder if you'll elaborate on it, is could this kind of a technique be used to assist in implementing something like a thread pool, something really far from the easily mapped state?
I maintain that it can. It's hard to demonstrate in this forum, but there's a couple things that very much relate. Oh, the question is this really applicable to really real-world complex situation? Is that a fair rendition? Yeah. I maintain that it is. I maintain in a lot of cases we're actually kind of doing it by accident already. Resource acquisition is initialization is really a similar idea in lots of ways, and we like that idea. It's just not related to abstract algebra, so it's kind of like ad hoc on a case-by-case basis. But the idea of making provably correct, demonstrably correct variables that can't be changed is, in matter of fact, it's even in vogue. The idea of immutable types is now a very popular idea which people are exploring. And immutable functions also for the same reason. And so if we start, this really encourages you, thinking like this, to factor your code into mostly immutable types, in which case, like, most of your problems go away. And then we're in the C world, we're not in the Haskell world, we're probably going to have mutable types somewhere, but we're not going to have them all over the place, because this kind of thinking kind of discourages you from doing that. I don't know if that's a good answer, but that's the answer you're getting. Tells me the session is over. There's no more questions, it looks like, so I guess we just perfectly in sync. I thank you everybody for coming, and I hope you enjoyed my talk.